We're talking about magnetic circuits and magnetism, and hysteresis is very important in the magnetic circuits that we use practically in, let's say, motors and transformers, etc. The performance of your electric circuit has very much to do with the hysteresis or the residual magnetism that exists in the materials that we use for electric circuits or for electric machinery. So in magnetics, we don't just have a magnet and then no magnet, have a magnet and then no magnet, right? In magnetics, sure, basics, there can be a magnetized material that sits on your desk and it's called a magnet, right? And that's pretty simple. But in the real world, we're using magnetism for lots of very interesting things that helped us industrialize, right? Motors, transformers, exploit the characteristics of the physics of magnetic fields that are constantly changing, that are constantly moving. This is how we generate electricity. This is all very important. So it's not about just being a magnet. It's about magnetizing and unmagnetizing, magnetizing and unmagnetizing. Now, why do we magnetize and unmagnetize? We magnetize and unmagnetize because we actually change current. And we can take current and it's at zero, and then we can apply a positive current in amps to a piece of electric machinery, and then that goes back down to zero, and then that goes back, then it goes into negative, and we apply a negative current, which is obviously a current of the same magnitude in the opposite direction. So that's just electrons flow in the other direction. Flow other direction. Which we don't really call negative amps, do we? We just say it's the same maximum amplitude, and it goes in one direction, then it goes in the other direction, then it goes in one direction, then it goes in the other direction, and it hits the same max in each direction. It hits max here and it hits max here, max. And then, so what we're doing in electric machinery, is we'll have a situation like this, for example, on a transformer, and I have a circuit here, plus and minus, and then I have a circuit here, plus and minus. This is the current primary. And let's say this is primary. So I actually control this, and this is me. I'm paying money to make this current, right? This is my choice. I decide to make that an AC current. So what this is that I drew here is an AC signal. This is AC current. I can choose the max and the min of it. And then my output over here, this is called secondary. And it's going to have a sinusoid as well. And depending on the number of turns of this, depending on the number of wraps of turns of this coil N and the number of turns I want to put in here, that's it. That will determine how much current I get out the other side. So depending on N in primary and an N in secondary that I decide to make here, it will depend on the sinusoid of current that I get out, current in amps that I get out on the secondary. Super cool, because they're linked. They're linked by magnetic fields that are called magnetic flux. And the magnetic flux is the linkage between the two. And that is amazing. And we can do so many things because of this, the link that is magnetic flux. Thank you, magnetic flux. This is amazing. However, what I do on primary doesn't instantly happen on secondary because the flux doesn't instantly get made. So as I go up, 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 up in current, then I'm going up, 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 up in H, because H is relative to current. It's N times I over a normalized length, right? So I'm going up, up, up in H. Well, we want this flux to get established up in flux, which is just flux per cross-sectional area, right? I go up in I, then I go up in flux, and then the flux links to the secondary in my transformer. Beautiful thing. Well, what's actually happening in our physics? We have to remember what's actually happening. Well, what's actually happening is that I am going from a material of these north-souths to be all misaligned, north-south, to all of the north-souths to be aligned, north-south aligned, and this is magnetic saturation. Well, this is a physical process. It's a physical process to align all of these into their boundaries, yes? And physical processes don't just turn on and off. This has a gradient and it has a lag. So I want you to remember it is a lag. If I were to ask you to write an essay about magnetic hysteresis, you would say it is the lag of all of the magnetism being established. And it is time. It takes time. It's a physical thing. So I yes want to put in that current, and we think everything happens instantaneously in magnetism and in the electrical world. But let's think about the physical things that are happening. It doesn't instantaneously happen. And it happens differently for each type of material as well. So sheet steel is going to get less cast steel has less flux density for the current going in, and etc. So it's different for each material as well. So it takes time for this to happen. And just like when I go back to zero on this curve, when I go back to zero, you expect this to be demagnetized again. So I go back to zero, here we go. Then if I have zero current, then I'm going to have zero magnetic field strength. Then I expect there to be zero flux, but I see that I still have flux. Well, why do I still have flux? Because I went from these nicely aligned north-south poles to now I expect them to be all disaligned. Holy, that's a big expectation because it takes time for this to happen. So I give it a maximum current in one direction, and then I go back to zero. My magnetism is not back to zero. It's got residual magnetism called retentivity. So I want you to remember the word retentivity. It is the retentivity of that material. Every material has a different material property of how much it retains that magnetic field, and that is called retentivity. And in order to get back to this fully aligned state, you actually have to give it a cohesive force. And that cohesive force has to be in the opposite direction. And that cohesive force that I'm going to give it in the opposite direction is actually going to be this part of the curve. This part of the curve. And it means that you're going negative. You're actually going to put some current in this opposite direction, go into negative H to coerce, to be cohesive and push this over here. And here we go. We're pushing it over here for it to actually get fully misaligned again. I'm just going to put a pause here for 1 second. So that's why this happens. Now let's walk through the curve. So let's look at A. All we're doing in A here is I'm saying, all right, I have no current. Now I'm going to turn some current on. So here I had no current, so I had no H. I turned some current on. I went to here on H, and look, my flux did not go just straight to here. It took me a while for my magnetic flux to develop. So here's my flux density increasing slowly because it takes time and there's a lag as a physical thing. So that's what we're doing in A here. So we understand that there's this lag. Now, as I increase current more and more, there's really no point in doing it because I'm not going to get any more B. B is pretty tired at this point. I'm not going to get any more flux out of this situation because of this material property. I have reached magnetic saturation, and I might as well stop there. So here I am at magnetic saturation, and I've come to my maximum H, which is, I went from A, which is right here, B on this this curve over here of AC current way over here. Now, so that's B. No problem. We reached saturation. We know what that means from our other videos about the BH curve. BH curve video. Watch that if you haven't studied that yet. Now, I say, okay, well, I don't want to saturate anymore. I know how the BH curve works. I know about residual magnetism. I know that I better go back down to 0. So I'm going to go down and take my current to 0 on this AC signal, which is going to take my magnetic field strength down to 0. So here I am there. This is C, and I'm down at 0. So I expect my flux, my amount of magnetism to also go down to 0. But then I remember, oh, actually, this is a mechanical phenomena. It's not going to go down to 0. It is going to have some retentivity. Whoops. It's going to have some retentivity. And then that retentivity is going to make it actually take some time. And here it is taking its time. It only goes to here. It only goes to here. It stops here. I'm going to get rid of some of this. So H is now at 0, and I only went here, and I'm not here, because of retentivity, residual magnetism that still exists. So here we are. Our signal is I equals 0 in this sinusoid that I paid for to go into this transformer, but the core of this transformer is now still magnetized. That's actually a good thing that it still stays magnetized. We exploit that in our electric machinery, and much of our electrical distribution system is based on the fact that this has retentivity. This is not a bad thing. We know how to deal with this. So we are still magnetized even though our current is at 0. Pretty cool. Now I need to apply a force. And if you were listening, you would know that that force is the cohesive force. So I better apply a cohesive force in this direction. Now that brings us on to point B. Here I am down here. I am now at, D. I am applying a cohesive force. A cohesive force is a force in the opposite direction. Current went to the opposite direction in order to force this highly retentive material into losing its magnetic flux. So here we go with that retentive force in D here. I put this much current in, I go down to 0, and then I put the maximum amount of current in down here. I am now at the very bottom of an AC sinusoid right here at D, and I have I max in amps in the opposite direction. Now, since I gave I max in the opposite direction, I forced there to be no magnetism. So when beta equals 0, we are here on this axis. This is beta equals 0. Magnetic flux density equals 0. That means it's no magnetism. So we have yes current in the opposite direction, but we have no magnetism. So you can see it just lags. It just lags. So instead of it going down to 0 here, it actually goes down to 0 here, halfway to the maximum of the current in the opposite direction, halfway to it. So I'll trace the curve. We expected it to go to 0 here, but it went to its residual magnetism, its showing that it has retentivity. Then we forced it out of that retentivity by giving it a cohesive force. Then it went to there. I still continued that current in the negative direction. I still continued that current in the negative direction to the maximum. I max in amps in the negative direction. My magnetic lines of flux started building up again. And those flux lines are now going in the opposite direction. They used to be going into the page if I took a cross section of the core of my magnetic circuit, but now they're coming out of the page if I took a cross section of the core of this magnetic circuit that I drew down here in the context of a transformer. So now they're coming out of the page. So those magnetic flux lines actually change direction. They change direction as well. So the magnetic flux is constantly changing. In order for the magnetic flux to be constantly changing, we're into Faraday's law, Faraday's principle, and you should really review the video on Faraday's law and Faraday's principle is really important here, because Faraday's law then says if there is a changing magnetic flux, then there's a changing induced current, and that's how we get our current in our secondary winding of that transformer. So now we're happily here with a lot of flux again, the most flux we could possibly have, but it's in the opposite direction. Great. We finally got there, but now we want to go back. So we go back to H equals 0. We expect this to go up to 0, but no, it has the same residual magnetism as it had before, because it's the same material, and this is based on the material property. So it only goes to here. That's E. And then that's when E is right here on this curve. And then now I have to give it a cohesive force. A cohesive force means give it some current in this direction now. And as I give it current in this direction now, I'm here on this AC curve, happily given direction in the other, given current in the other direction, and it follows suit to mechanically lose its magnetism. Oops, drawing it in the wrong spot. It mechanically loses its magnetism to be no magnetism. It's just instantaneous. It doesn't mean that we stop all current at this point. It just flies through that 0 point, and then it gets positive again and establishes magnetism again. And now we're at the top of this AC curve. What's this one called? G, at the top of this AC curve. So in conclusion, I'm putting a sinusoid of current in amps into the primary side of a magnetic circuit. Because that is a changing current, it's inducing, Faraday's law, it's inducing magnetism inside the core, magnetic flux lines in the core. But those magnetic flux lines are also growing and collapsing, growing and collapsing. So Faraday's law is telling us that on the secondary side of this transformer, it's also going to be inducing a current on that side. Well, I only paid for the primary side. I got out the secondary side. Holy, I can just wind a different number of windings on one side and the other side, and I can actually change the current. And if I change the current, I can change the voltage. And that's why this is applicable to real life. Because now I can step up voltage and I can step down voltage. Now, it does this because I can change direction as well. Lenz's law. Lenz's law describes the direction that we're changing. So at this point, you should be able to watch the video on the BH curve, watch the video on Faraday's law, watch the video on Lenz's law, and put all of this together and figure out how a transformer works. That's pretty cool. In summary, we have now gone like our hysteresis loop. We kind of ignore this first little part. Okay, we did have a first little part that went over here. We went from 1. We kept some residual magnetism. We went to 2. We finally got down to 0. We went to 3. we got as magnetized as possible in the opposite direction as per Lenz's law in 4. We tried to get back to 0, but we only got to our retentivity spot. That's 5. Then we finally got back to 0 here. That's 6. And then we got as magnetic as possible on the other side, which is called 7. And that entire thing that we did, if I were to fill it in, that is called the hysteresis loop of a magnetic circuit. And we go from 1 to 7, and then 1 to 7, 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 constantly around this loop in a real magnetic circuit, like a motor or a transformer. And since it's constantly changing, we are constantly inducing magnetism, and we're constantly inducing current, therefore making useful electric machinery. So that's the hysteresis loop of a magnetic circuit.